Section 3. Container Platform Tools. In Section 3, you'll learn about the open source software that manages the container platform. Part 1. Terraform and Ansible. There are more than 10 open sources used in K-PaaS container platforms, as shown in the table in the textbook, which are Kubernetes, KubeEdge, Harbor, MariaDB, Keycloak, Terraform, Ingress, Istio, Kubeflow, Vault, and Rook. Each of these open source software serves a different function. Let's take a look at a few of them that perform key functions. First, we'll look at Terraform and Ansible, but before that we need to understand the concept of coded infrastructure. Traditionally, it was common for developers to run bash shell scripts listing the installation of packages, modification of configuration files, etc. to configure the same environment on Linux. As IT has evolved, infrastructure environments have shifted from data centers to cloud environments, and the number of servers that a single administrator needs to manage has increased. Therefore, many servers in a cluster need to be deployed at the same time, and bash shell scripts have become limiting. The concept of coded infrastructure was designed to solve this problem. It means that the deployment and configuration of an environment is defined and used as standardized code. Deploying infrastructure as code means that you can break your infrastructure into modular components and combine them in different ways through automation. In other words, you manage and provision your infrastructure through code rather than manual processes, so you don't need a separate set of infrastructure to manage your information. What are the advantages of using infrastructure as code? For starters, it abstracts the details of your physical environment, so you can focus on the code that matters. It also requires fewer server resources than manual configuration, which can reduce hosting costs. Deployments are faster and errors are reduced because developers don't have to manually manage infrastructure every time they create an app. Finally, infrastructure consistency is improved and configuration drift is eliminated. Because of these benefits, coded infrastructure has become an integral part of continuous integration. Terraform is a leading coded infrastructure, developed and operated by HashiCorp, that makes it easy to build, securely change, and efficiently manage the shape of your infrastructure. Terraform is platform agnostic and as a provider offers a wide range of cloud services. In addition, whenever changes are made to the environment, the current configuration is replaced with a new configuration that can reflect the changes, and the infrastructure is re-provisioned. Terraform is characterized by four main features. First, it's a coded infrastructure, which means you can define your infrastructure in code to increase productivity and transparency, and you can easily share the code you define to collaborate efficiently. Second, by separating change planning from change implementation, you can reduce the number of mistakes that can occur when applying changes. Third, you can see in advance how small changes will affect your infrastructure as a whole, so you can build a dependency graph plan based on that graph and see how the state of your infrastructure changes when you apply your plan. Fourth, you can automate the deployment and change of infrastructure with the same configuration in multiple locations, saving time and reducing mistakes. The second is Ansible, which does something similar to Terraform. Ansible is software developed and operated by Red Hat. Ansible is an open source tool that automates many manual processes, including provisioning, configuration management, application deployment, and orchestration. In short, it's an environment configuration automation tool that allows you to manage multiple servers efficiently. Ansible's main feature is that you can declare the configuration you want to run in a playbook, and it will automatically run it whenever you need it. By declaring a configuration for a web server and a configuration for a DB server, administrators can deploy the server's settings according to that configuration whenever needed. Next, we'll compare Terraform and Ansible. Before we dive into the differences, let's talk about what they have in common. They can provision a new cloud infrastructure. They can configure the same required application components. And they can run remote commands on newly created virtual machines. In other words, Terraform and Ansible don't require a separate set of infrastructures to manage health information, so both tools are characterized by mastery. Now let's get down to business and compare the two tools. Since Terraform is an orchestration tool, it provides a comprehensive solution for infrastructure management, provisioning and deprovisioning infrastructure based on declared resources using cloud provider APIs. Ansible, on the other hand, doesn't offer as comprehensive a solution as Terraform. It's primarily geared toward configuration management, keeping your applications and dependencies up to date. Next, Terraform and Ansible each have a declarative and procedural, respectively. Terraform is used to write coded infrastructure, while Ansible uses YAML syntax to define procedures to be performed on the target infrastructure. Terraform uses HCL, HashiCorp configuration language, which is declarative, so the order in which the code is written doesn't matter, whereas Ansible YAML scripts are procedural and run downward as you write the script. Terraform stores Ansible scripts in Ansible playbooks, although code can be spread across multiple files. No matter how you write your code, Terraform identifies dependencies and provisions your infrastructure. If Ansible needs to perform a specific sequence of tasks, it defines the same tasks in a playbook, and the tasks are performed in the order they are written. Finally, while Terraform makes it easy to write existing infrastructure or convert it to code, Ansible requires you to write a user creation step before defining an installation task. If you want to install an Apache server on a virtual machine designated as the root user. Next, let's compare the two based on changeability. First, Terraform takes as input the desired state of the infrastructure, which can be provisioned. Ansible is unchangeable by default. Additionally, Terraform will change the infrastructure if the cloud provider cannot implement the change without rebooting or replacing the infrastructure. In comparison, Ansible does not allow changes to replace the underlying infrastructure. It can only repair or modify the configuration of specified components. Finally, Terraform removes old infrastructure components and replaces them with new ones that have the latest configuration settings. And because servers managed by Ansible keep a record of the configuration changes they make over time, different servers can have different configurations if not properly managed. So, which one should you choose between the two? Terraform comes with excellent scheduling capabilities, provides a very pleasant experience for users, and has good integration with Docker. But the downside is that there is no clear evidence of how the target device ended up in its final state. Ansible is a more mature tool as it offers better security and access control list capabilities, and aligns comfortably with traditional automation frameworks, but is less suited for services such as logical dependencies, orchestration services, and interconnected applications. Part 2. Vault. The second open source software we'll look at is Vault. Vault is a cross-platform password and authentication management system from HashiCorp. It offers interfaces such as JavaScript and CLI, and provides a secure way to use stored secret information. Vault's storage backend is responsible for storing encrypted data, and is not responsible for the type of storage, availability, etc. The components of a vault can be categorized into 5 main areas. First is auth, or authentication. As shown in the figure, you can authenticate in a variety of ways. From the most basic, username and password, to delegating authentication to a trusted third party, such as GitHub. The second is the core, which is where the encryption algorithm is implemented and routing for permissions takes place. The third is the secret. Secrets support a variety of services and can be as simple as a key, value, or as complex as a DB engine. The fourth is storage, which is needed to store tokens, policies, and configurations. And finally, audit. This is where we log all the requests and responses coming in and out of the system to keep a record of what's going on under the hood. To simplify the structure of a vault, the client sends a token and a secret path to the vault. The vault has the data the client wants, the secret information. Vault checks the client's token permissions and, if allowed, returns the requested secret information. You can think of this as 3 main steps. Part 3. Ceph. The last open source software we'll look at is Ceph. Ceph is a storage platform. It implements object storage on a single distributed computer cluster and provides storage capabilities at the object, block, and file levels. It aims to address fully distributed operations with no single point of failure and is capable of scaling out to the exabyte level. There are three main reasons to choose software-defined storage like Ceph. First, your application can choose the performance and cost trade-offs of different hardware and endurance configurations using the same software stack. Second, flexible interfaces allow you to choose industry-standard APIs, embed client libraries in your application, or use proprietary APIs if needed. Third, you can implement a variety of storage, reducing R&D and operational costs by utilizing the same storage software stack across object, block, and file abstractions. Finally, the structure of Ceph. The Ceph OSD daemon is responsible for storing data on behalf of Ceph clients. Next, the Ceph monitor maintains a master copy of the Ceph storage cluster map for the current state of the Ceph storage cluster. Third, the Ceph manager, instead of the Ceph monitor, maintains detailed information about the data, which greatly improves performance at scale. Finally, metadata servers are responsible for storing metadata used by Ceph FS for efficient command execution by clients. This concludes day 2. On day 3, we'll learn how to build a container platform cluster, portal service, pipeline service, and source control service. Thank you, everyone.